Hi, I'm Joe Pineda. Pleasure to be here tonight with you guys. It's my honor to introduce to you two speakers. First will be Pavlina Karafillis, and second will be Daryl Freund, and I will end up tonight's show and tell session. Pavlina is going to talk first. She's going to discuss solar, unique uses of solar energy, things that she's actually experimenting with herself. Pavlina has a distinguished career at Caltech, supporting JPL and the Perseverance rover that's currently on Mars. So please welcome Pavlina Karafillis.
I believe that there's a picture I will be able to talk to. So there we go. If folks are confused by this, they should be. So I ordered in the mail maybe a year ago now a 10x zoom lens, and I quickly realized that I could use that to burn small wood panels. So I wanted to figure out a way to use that. So I started by buying a 3D printer, which is what you'll see at the top, and making a little fixture to hold that lens and making it set up appropriately so that I could use a 3D printer to take any pattern I wanted, put a piece of wood in there, and wood burn any pattern I want. So I'm able to grab a little piece of wood and pick a pattern in there, get a pattern, put in the 3D printer, and print any pattern I wanted. I realized that if my prints were longer than, I don't know, 15 minutes or so, which sometimes they are, especially if the pattern's a little bit complex and you want to have a nice solid line, so you go slowly. What would happen is that the lines would be disconnected. So where the printer started, it would never really end up in the same spot. And I believe this is because the sun moves. It may be an elementary fact to most people, but it took me a minute to figure out. And I realized that I needed to track the sun as part of this printer. So the ridiculous object that hopefully we're sharing, okay, is the setup of stacking. I have a tracking mounted home that I use for my telescope, which is really a camera, but I use it to be able to take cool photos. So I said, wait a minute, I have something that already tracks the sun. Why don't I put that as my base and then take my device and put it on top? And therefore I should be able to track the sun with my base and put on top my wood burning solar power device. Now what's really cool is if I have some batteries that are also solar that I can charge with a little solar cell, so I can make the entire thing solar powered if I want to. For testing, I plug it into a wall because that's much easier. But at some point, so what you're seeing here is the rope is because I'm trying not to cut wire, the pink cable because I'm trying not to cut wires and eventually be able to bring it back to a 3D printer that functions, which is why the cute little pink thing is on the side. But at the top, you'll see the 3D printer with the cylinder that holds the lens that focuses the sunlight and burns the wood. You'll see the 3D printer shape. It's like the cheap 3D printer you can buy. And underneath it, you'll see something that gives me my angle to the sun because I don't use both axes of the tracking device. I just use one axis to spin. And then finally at the bottom is my tracking device that I use normally to just track the sun. So yeah, this is a ridiculous fun idea that I had and I tried to execute on. It's a little bit insane. And every time I bring it to people, they say, laser cutters exist. I do know they exist. I'm just having a little bit of fun. Yeah, if there's any question, and full disclosure, I tested each part separately. I've stacked them. And I haven't put them together yet just because I'm not there yet. I didn't get that together in time, unfortunately. But figured this was a ridiculous thing that might be fun to share. Does anyone have any questions or many concerns as I have? I see Dana has her hand up.
Yes, so is the answer safety ever been a sound?
No, so I'm not actually producing an image with the lens. The lens it's basically functioning like a magnifying glass and like burning ants sort of deal. That's what the lens is doing. And I can use a 3D printer to program whatever pattern I want. So I let the sun make the line. It basically functions as a laser. And then the 3D printer moves that line around to make whatever, I can make it into a butterfly, an ant, a heart, whatever you want, right? Yeah. Yeah. I think I saw one more hand at some point as it disappeared. All righty. Thanks for listening. Appreciate it.
So our next speaker is Mr. Daryl Freund, a member of DAS. Daryl has a long history in geospatial imaging. For many of us, the pretty pictures that our group builds with photographs like you see on the wall there are beautiful to look at. And for some of us, color is data. So tonight, Daryl is going to talk about color calibration of astro imaging cameras. Daryl Freund, please welcome.
Hi, my name is Daryl Freund, and I'm going to talk about doing color calibration of an astro camera, similar to what is done with digital SLRs. Okay, so I've been retired since 2016. Yes, thank you. But in my last assignment, I was working on characterizing debris in the geosynchronous belt and was involved in writing a lot of MATLAB software to do image processing. So when I retired, I decided to write a processing pipeline for digital SLR processing of astrophotos. So basically what I developed over a number of years was code to read the raw images, dark and flat correct images, color correct them as done for digital SLRs, identify stars, register multiple images, and do the rest of the processing, stacking, and so forth. So I started seeing this discussion about this missing color transform for astro cameras. And I was kind of curious about that because I had to implement this same kind of color correction process for my digital SLR. So I sort of made this post-retirement project to look at this with the astro cameras not really, or the manufacturers not really providing the data to do what's done with digital SLRs to correct color so that it looks like what the eye would see. So, okay, other way. So the basic idea is a person looks at some scene, which this is from the balcony of my condo in Denver, and sees something, and the eye has a basic spectral response to what they see. So when you take a picture of a camera, of course, it has a different spectral response. And so if you want to look at an image process of that and see something similar to what your eye would see, there has to be some kind of processing or transformation to get from the output of the camera to an RGB image or a display or something of that nature. Now, for digital SLRs, the manufacturers have done a great job at doing that, and it's pretty seamless. For example, you take a picture of your iPhone and look, it looks pretty much like what you just saw. But this transform process for astro cameras apparently is missing. And so what I focused on was generating the data to do this transform for the specific camera that I had, which is the ASI 533 MC one-shot color camera. So the industry developed a long time ago this thing called the XYZ color space. And it was basically a derivative of researchers a long time ago trying to understand the response of the human eye. And they take this monochromatic light source and shine it on a white background and then ask various observers to take a combination of primary colors and try to duplicate the same color as the monochromatic light source. And they did this across the visual spectrum. Well, of course, there was a bunch of problems with that, and it wasn't quite so easy as that. But the bottom line was, out of that, there was developed these color matching functions that sort of was a representation of the response of the various cones in the eye to the stimulus from the spectrum. And the XYZ color space grew out of that to be a mathematical representation of this, in a device independent manner, such that if a camera took a picture of something and then you took the raw data and you transformed it to this XYZ color space, there then existed a known set of transformations to take that and move it to an RGB, whether it's sRGB or Adobe RGB or whatever. And this could be done for any camera, and any camera that produced the same XYZ transformation would produce the same color on the output. So this kind of became a basis for color management in the digital world. So the goal then would be to develop this transform for the Astro camera. And then once this transform is developed, we could take the raw output of the Astro camera, transform it to this color space, and then transform it to an RGB image. So what do we have to do that? Or how do we do that? Well, yeah, well, again, the industry provided all the tools to do that. And in fact, serious amateurs and professionals that do color managed workflows do this sort of thing. And there exists these calibration charts that have a series of colors on them with known responses in this XYZ color space. So the idea is you take a picture of this and then you figure out what you have to do to transform the camera response to the colors, to the values in the XYZ color space. So there's a little more, few more steps in that, but that's the basic idea. So what I decided to do was to do some baselining with my Canon R6, figuring if I couldn't get that to match, then I wouldn't really be able to go any farther. And then I did it for the ASI 533 with no filter, a UV IR cut filter, and the Optilong L Pro, which is a broadband pollution filter. And so to give away a little bit of the rationale here, the reason you really want to do this is because the result, at least with terrestrial images, is dramatically more vibrant and colorful images. So, okay, how do you measure this thing? Well, you have this very scientific setup here to begin with, where you take a picture of this chart, this color checker chart. You calibrate the images with darks and flats. You mosaic the image because the one-shot color camera has this thing called a Bayer matrix. So it has individual slots for red, green, and blue. Then the first step is you have to identify where all these patches are in the images and measure the RGB values for each of these patches. Then you have to white balance the image, which basically essentially means to make adjustments so that the RGB value for the gray values across the top are all equal. So once you've white balanced it, you get this next one here. Now, at this point, you measure the patches again for each of the colors in this patch, for which there are known values in XYZ color space, and then run regressions or other optimization procedures. I did several different ones to transform the responses from the camera into this color space. Now you see this looks really weird, is the XYZ color space isn't really meant for projecting. It's more of a transition space to convert the camera response into something similar to what the eye would respond. And then from there, you can use a known transform that's been published to transform that to the final result, which is here in the bottom. And you can see just from the white balanced image in the top to the image in the bottom that the colors are a lot better. So The basic idea for the calibration is take the raw image, dark and flat, correct it, demosaic the image. Then the two things that you need from that calibration step are the white balance to go from the second in the middle top to the right, that, and then the measured XYZ transform that we did. So we apply the transform. Then there's two other steps, but this is from data that's known and published, is to take what we've transformed to XYZ and transform it to an RGB, such as sRGB, Adobe RGB, ProPhoto, whatever version you want. White balance it. Then at this point, the image is still linear. Apply the gamma to it, and then go on to do whatever else is needed. So at this point here, I'm going to show some samples of what I did with the ASI. Here's my setup here on the balcony taking the pictures. This first one here is raw from the camera, what just came out, and I put it on the screen. This next one here is after the image has been white balanced, the first step from the measured process. This is how it's been transferred to the XYZ color space after it's been. And then this is the final step here. So you see, going from the white balance to the final calibrated, it looks a lot better. Now, the one thing I want to point is you really can't get to here by just white balancing, because when you do the transform to XYZ, each of the XYZ coordinates is a linear combination of the original R, G, and B outputs. So that's kind of the key step in this whole process. So at this point, I'm going to show some other samples of this. This is for the 533 with the Optolong Pro filter. This is a close-up of the just white balanced, and then the full calibration over here. This is for the UV IR cut filter. Again, this is just the, just the white balance and then the full color. And you can see the color is a lot more noticeable. Now, if you just increase the saturation on this white balance, it doesn't really look that great. So there needs to be more that's done, at least in these particular instances. This is with the white balance only, with the R6 and the full calibration. And fortunately, it did look pretty close to what I was able to get with Photoshop, or Lightroom, or Raw Therapy. This is with an open filter, which I'll make a couple comments on. This has a little bit of an IR look, and this particular camera doesn't have a UV IR cut filter. When I first looked at this, I was scratching my head, as wondering why the trees aren't green. I did some thinking on this and realized that the green leaves have chlorophyll in them, which strongly reflects in the 700 nanometer to 1.1 micron range, roughly. And so that changes the color. And in fact, some of the colors of objects that reflect strongly in all the out of band areas will affect the color a little. And so if you look here, the difference between the no filter and with the UV IR cut is quite dramatic, but still it looks pretty good with the no filter, just for overall balance. So I took some astro pictures of this, and I did this with my Canon R6 because I got this, I wanted to try out this Optolong Pro filter. I went out to the dark site last month and imaged these images. These were completely processed in MATLAB, including the dark and flat correction, registration of multiple images, stacking, and then the stretch. I also programmed up the Roger Clark stretch algorithm, which was applied here. And so you'll notice there's quite a bit of color in these. This was the actual setup that I used here. There might have been a little bit of aurora, something going on there when I did it. I was really trying to get the comets, and so I did get those. This is the R2, and this is the A6 over on the right, which was about right here on the horizon. So I think I don't know if I would have gotten anything without the light pollution filter. Okay, so a couple thoughts on this. I just used the ASI Studio to capture images from FITS files for the Astro camera, and I didn't really cover this, but I used the standard procedure and the strolls with my dog blog for how to do the calibration methodology for the Astro camera, and the XYZ transforms here, and I just pretty much follow a lot of guidance and all of that. I tested several different methods to obtain the XYZ transform, but the one I actually preferred the most was the Strolls optimization algorithm, which is a optimization as opposed to a straight linear regression. In summary, I did have some degradation with these Optilong Pro filters with the fast system. And I didn't really talk about this, but I did look at the errors in these, and there's these DEOO errors, which is basically a measure, an industry measure of the difference between what your transform produces in the XYZ versus what it actually should be. And for color managed workflows, generally under 3 is good. And so for the clear digital camera, did really well. For the Optilong Pro, which does have some notches in it, did pretty well for the R6, which also has a UV-IR cut. And then the UV-IR cut did pretty well on the ASI 533. And these other two did okay on the ASI 533. So I think the calibration of these definitely improved the color for the terrestrial images, which I had a comparison for. And I'm assuming it probably would have improved the color in astrophotos. I did try to calibrate a couple of narrowband filters, but I quickly gave up on that because they would have almost no response, say in the blue channel or whatever. That kind of made this whole thing pointless. But the takeaways from this is this calibration data only needs to be done once for each configuration, just like for your digital camera, the transforms are baked into the raw images so that when you use Photoshop or whatever program you use to read them, the software reads that data and processes the images with that data. So it also requires the application of 2 3x3 transform matrices, first to go to the XYZ and then go to the RGB, along with 2 white balance steps. Now, I believe these can be done in PixInsight using pixel math, but I've never used that program, so I'm not really positive. So next steps, I can share this information, the transform values and so forth for anyone who has an ASI 533, but I would be willing to work with folks who are interested to test this for their particular setup. In that case, what we need to have is take some images of this color checker card, as well as darks and flats. And it might be interesting to take some images of some scenes to see how it does. To generate these two things, the white balance and then the XYZ transform. And then the rest could be programmed in whatever program you use to process your images. I think that I don't see why this wouldn't work for monochrome cameras using RGB filters or LRGB filters. But those filters might be more conditioned so that this is less necessary than with the Bayer matrix. It still might be interesting to see what the difference would be. Okay, any questions? Yes.
Did you use any toolboxes in MATLAB, or was it all native code?
I have the imaging toolbox, and I used their algorithm to de-interleave, to demosaic the image. I started writing my own code to demosaic the image so I could use the specific algorithm I wanted, but it was kind of slow compared to what the MATLAB version was. And what else did I use? A couple of things, but some of the steps in the workflow for a conventional digital SLR are a little bit different. So I couldn't use their routines because they do things a little differently. So I had to write a lot of my own code, but I did use some code. And then also, let's see, did I measure? Where was it? I did use some I tested some of the optimization algorithms here and the data from here, and I wrote my own white balance. I may have used the MATLAB Bayer to planar, which is how you pull out the individual colors. That's pretty much it, though.
So my goal tonight is to give you something that might be fun to do. I did a little DIY project, astronomy related. So what I wanted to do originally was construct an all-sky camera. Construct an all-sky camera and make it myself, 3D print a case and put a plastic dome on it, use some cheap components and see if I could get it to work. I wanted it to run off 12-volt power, so if I'm at a star party somewhere and somebody's got 12 volts, I can use that. I didn't want to write any code, which is fortunate because it probably wouldn't work. And I found somebody online that has written one. So the credit is for a Mr. Ian Knight, British astrophotographer. I'll talk about it, he was with the British Astronomical Association, and he's a career software developer. He lives in the Netherlands, the northern part of the Netherlands, and so his website is astroisk.nl, which I guess means Netherlands. So I took his software, I added some extra wrapper code around it to make it work with the Wi-Fi and so forth. And I created an image file that you can download yourself if you want to do this. And I'll show you how to do that now. So the features of this is real-time image capture, 180-degree field of view, using a Raspberry Pi high-quality camera and lens. It uses a Raspberry Pi Model 5B CPU using Bookworm as the OS. Time-lapse video, star trails, still images, kilograms, and I'll explain what all that is. Image stretching and exposure control. So it's not just a camera. There is a little bit of image processing going on inside the software that will stretch an image, and you can program where the stretching point occurs. His software is compatible with multiple cameras, including ZWO. But I used the Raspberry Pi high quality camera, and I'll explain to you what that is. The software is free, open source, and has community support. It's mature. I didn't really have any trouble getting it to work. Let's see. So since the software dictates the design in this particular case, I have a 12-volt supply at the lower left feeding into a DC to DC converter, which takes the 12 volts and turns it into 5 volts. The reason is if the power supply is far away from the camera, the voltage drop across the cable, the power supply cable, won't impact the operation of the DC of the Raspberry Pi. I have a USB memory stick connected to the Raspberry Pi, 256 gigabytes, $23 for that. The Raspberry Pi, $88 with a heatsink and fan. The high quality camera, $53. Wide angle camera lens, $25, and an acrylic dome. So the total cost for just the most expensive parts that you see in the block diagram is about $235. The camera is a Sony IMX477R back illuminated sensor. It could be a good camera for, say, a guide scope if you're doing astrophotography guiding. 12.3 megapixels, and I'm using it with 2x2 binning, which means I have 4 pixels added together to make 1 pixel, a big fat pixel. So it's sensitive to light. And it has an M12, which just means it's a thread, a metric thread, M12 thread on it that you screw in a lens. So it's pretty simple there. So this, on the right, there's a table with all the different modes the camera will operate in, if you're interested. The lens that screws into it has across a rectangular diagonal, has a field of view of 184.6 degrees. So pretty good. And the rest of the data on this is, it's that first lens on the left there with the green arrow. And so basically the field of view X by Y is 140 degrees by 102 degrees. So it's not quite 180 degrees X by Y. I designed a case in Autodesk Fusion 360. It didn't take long to do. It's just 2 parts. They snap together. It's a can and a lid. The lid hosts the Raspberry Pi computer, the camera, and most all of the guts in the thing. The lid does. And then the can just has a little DC to DC converter and some connectors and keeps the rain off the electronics. I used a Polylite ETG filament, which isn't quite as good as some thermoplastics, but it is weatherproof, or at least so far it is. Time will tell. And it prints real easy. You don't need a closed frame, really expensive printer. I did use one, though. I used a Bamboo Labs X1C printer and some PETG filament. PETG is it's an acronym. It stands for, I think, polyethylene tetrophthalate glycol. And it's the same stuff they use to make plastic Coke bottles out of. Let's see. So the guts. You can see here that there's a lid. It has a Raspberry Pi sitting on 3 posts. And there's pre-drilled or pre-printed holes in the post that you just screw the Raspberry Pi down to. And then there's a heatsink and fan that snaps into the Raspberry Pi. And then there's that ribbon cable that you see there that connects the camera underneath to the Raspberry Pi. So this whole thing goes together in about 30 minutes assembly time. The print, it takes about 3 hours and 30 minutes. Does that show up for you guys? Yeah, it looks like it a little bit. So there's a lid and a can. It takes about 6 hours to do both. If you use the PETG HF, about twice as long, 12 hours, if you use Polylite. The software, so I used an OS that comes from the Raspberry Pi Foundation called Bookworm. They have a new one that came out in early October called Trixie. But I had trouble getting it to work with Trixie. It probably has to be recompiled anyway. So I have built the whole thing software-wise And when it'll ask you to log in, the username is DAS, DAS, and the password is DasBoot. It has a VNC interface, which means you can remote into a Windows desktop, and like in the lower right, it looks like a Windows type of desktop. And it has SSH, which stands for Secure Shell, so you can do TTY like type, alphanumeric commands to get it to do stuff. And then the AllSky software itself has a web page. And supposedly you can make this remotely accessible anywhere in the world. I haven't done that yet, so right now it's local to my house. But I do have some demonstrations. I actually brought the thing tonight. It's over here on this table. If you want to come up later and look at it, and I can unsnap the lid and let you see the innards. So first results. So here is an all-night time lapse from my house. I have the unit sitting on the top of a 55-foot mast connected to 12 volts via a 150-foot cable, and the voltage drop did not seem to be a problem. That's the moon going by. My house, using an SQM meter, is about 19 mag per arc second square, so not quite a dark side, but not too terribly bad. So in that image, there is, you can, well, I'll just jump to the star trails. Let's just go to that one. So it can also do star trails. So what you do, the only knob you have to turn with the star trails is how bright you will allow the image to be considered a part of the star trail. So the Earth rotates once every 24 hours. So you would see, if it was letting everything in, you should see a half circle for the stars. In this case, I had it reject the moon, a lot of the images, so the star trails are a little bit short. But you can see where the Polaris is, and you can see fragments of surrounding terrain in the corners. A kilogram. So this is useful as a tool for astrophotographers. What it does is it takes the center pixel of your camera, your astrophotography camera, and it takes top to bottom in that center pixel, all the vertical pixels in that center spot. And it adds them together over the course of a night. And so what it does is it gives you an idea over the course of the evening if there was a problem like clouds, some neighbor's lights, a car going by, and dusk to dawn. So this is a sample image of what a kilogram does on the left, and with arrows pointing to what you're looking at, and the actual image from my camera. So in the center there, that's the moon essentially going by, and then you can see a few clouds on the right, and you can see dusk and dawn on the left and right. So it was a reasonably good night. And then you can capture still images. You could do it for daylight too. So if you got an eclipse and you want to do a time lapse of an eclipse, you could do that. The cost. The cost is about $304.73. That's what I paid for it. If you decide to build this, I have sections in this presentation, which I'm not going to go through because it'll take all night. But you can use this to build one for yourself. And I've got details to do it. So I'll just step through it real quick. The can and connectors to assemble the can, there's two connectors and an LED. The LED is glued in place. The connectors are screwed in. Then there's the DC to DC converter, costs $10. It's potted, so it's weatherproof. And there's I have a little splice there, butt splice with levers, so there's no soldering, so you don't have to do any sophisticated work on it. The camera, you do some unbolting and taking some parts that you don't need, like a tripod adapter. There's a ribbon cable, and the 3D print has 3D printed holes, so when you screw in the screws that hold it in place, they go in easy. And then the assembly of the Raspberry Pi to the lid is the same process. It screws in, and then you just connect the ribbon cable to the Raspberry Pi to the camera. There are only two cables, two wires. There's two cables essentially that connect the lid to the base of the can. One is an Ethernet cable, 6 inches long. The other is a power cable carrying 5 volts to the Raspberry Pi. The Raspberry Pi has built-in Wi-Fi, hotspot, Ethernet, all that. and then you download using the Raspberry Pi imager. You can either use the image I had, or you can make it yourself. Online on our DAS OneDrive, all the CAD files for printing the can and the lid are online, as it is the image file and this presentation. Let's see. This is just how you write it all to a USB stick. The USB stick gets plugged into the Raspberry Pi there where the yellow arrow is. There's a first time power up. You check your wiring. Red goes to red, black goes to black. There's not much wiring to do. And then you power it up and you try to log in. And it's really simple. You're just looking for this prompt down here at the bottom, and then you send a command over your secure shell to test the presence of the camera. It'll tell you, and then you're good to go. Then you shut it all down, and you put the can and the lid together and do that test again. Make sure nothing got in the way or nothing came loose. Then you configure the Raspberry Pi. And then you launch the software. The guy from the Netherlands wrote, and it's very, very well done. It's got all the settings you can control. It's got all kinds of ways really do make it easy. I made some changes to the basic settings. Those settings are in the image file that's in the OneDrive. And they're the same settings I used to get the imagery I just showed you. Once you have the camera focused, there's a procedure for doing that. You put a ring, there's an inscribed ring on the lid for putting some silicone sealer there. You put a ring of silicone sealer there, then you bolt the acrylic dome down to the lid. And then if you want to, as time goes by, OSs change and everything needs to be updated, you may want to build it from scratch. And so I put a procedure in here for doing that. It's kind of cryptic, but it's Linux, based just Linux commands for loading things. That's all there. And then finally, you want to be able to download the data, the pictures from your Raspberry Pi all-sky camera. And so you load a program called Samba onto the Raspberry Pi. There's how you do it. And then you can use in this case, a Mac I have here, you connect to server. And then you put the directory from the Raspberry Pi where all the imagery is, and you just download it. And let's see. What can go wrong? You can get a bad power up. The Raspberry Pi 5 is very picky about the rise time of 0 to 5 volts. And what I do is I just cycle power. That fixes it. It doesn't actually create an images directory, and sometimes you get an error message until you actually save your first image. And then if you reboot or have to reload the software, it doesn't like that because it sees a different log on, and this is a way to fix that. Questions? Okay. Oh, I'm sorry. Go ahead, Dina.
So if you're interested in meteors or bolides, do you have to manually scroll through the data to find them?
If you're interested in...
Yeah, in capturing a meteor or a bolide or
yeah.
fireball.
Yes. So what it does is there's a directory on the Raspberry Pi, and I can show you that here in a second, where all the images over the course of the night are stored, and you may have hundreds depending upon the refresh rate that you program in. And you could capture one, or you may see Betelgeuse blow its top or something of that nature. You might want to just capture that, or the blaze star, or I don't know, a comet, for example, might be interesting.
Okay, so there's you didn't create it with some kind of a sensor if the light went up dramatically in a very short period of time to capture an image like that?
No, there's no trigger for that kind of event. You can set thresholds for minimum and maximum mean luminosity in the image. That's what you can do. But like a pinpoint star probably wouldn't trigger something like that. You'd have to see it in the morning.
Thanks.
Yeah, sure. So this is it over here. And I've been taking images since we arrived. So let's just see if we got anything. So I am, oh yeah, there it is. Who's that crazy person? And so this is the most recent image from the device. It's right here. It's running off 12 volts, and all I did was plug it in. That's all you do. So it's very simple to use. And then if you wanted, I think, Dina, to your question, you can go to the images directory. And so in the images directory, this menu option here, you can see images, time lapse, keogram, and star trail. So if I call up, say, a time lapse, and this is an old one from my house. Oh, that wasn't it. Let me go to a different one. Oh, there it is. So this would have been an iffy night. I would have probably gotten some images with the refractor, but then the clouds rolled in. That was taken on the 11th. And then, say again, please. I don't know. I'll have to check. So what I can tell you is it's taking one image every 90 seconds in this particular case. Yeah. And you can program that you can set a delay between each image, and you can set the maximum amount of time per image, and that would set the rate of imagery that you get. Now, as far as the playback speed goes, I don't know. I haven't tried to play with that particular thing yet. And then let's see. Keogram. This was taken on the 8th. That was that image I showed you earlier. And star trails. Yeah, that also was from the 8th. So you can download these using Samba to your PC. And there you go. Any other questions? Thank you. I hope if you have any questions or like to see this demonstrated, I'd be happy to show you.
Did you explain the keogram to the group?
Yes, the keogram. So the keogram is a tool. What it does is it takes every picture that you take, and it takes a vertical stripe of pixels from the center of the image and puts that as a function of time into the picture. And so what you use that for is an estimate of when, if you had problems with your imagery, when did they occur? So keogram, let's look at the first one. So here's one. This is another night with a full moon. You can see on the left there, it was transitioning between day and night, so the imagery was a little dark, but that was sunset. And then I had this set up for automatic exposure and automatic gain. I have since learned that you don't want to do that. You want to set a specific exposure and specific gain. So that's what these alternating bands of black and white are, or black and blue. And then over here, you can see that there was a lot of cloud cover on the right, in addition to the moon. Does that make sense? So it's a tool. It's like a histogram of what went on overnight. Okay. Thank you so much.